So fundamentally, trigonometry is really all about angles. And you might say, well, I already did a bunch with angles in geometry. Why do I have to do that again? Well, the truth is in geometry, angles are evaluated differently than they are in trigonometry. They're stagnant, they float around in space, and the discussion about them is really more about their measure than about their behavior. And trigonometry is cool. It starts to look at what is the behavior of an angle. So first thing we have to do is look at them differently. So in geometry, an angle would have two rays, right? And an angle between the two rays with a vertex. And you may have talked a little bit about initial and terminal rays, but really there would be no reason for that because you don't really care whether the angle went swooped through from this ray to this ray or from this ray to this ray. You only care about what's the measure. But in trigonometry, we care a lot about the direction that the angle took to get to its destination. So first, let's just do some terminology. An angle in trigonometry is one in standard position. Is one that has the vertex at the origin. It has a ray that is locked onto the x-axis. This is called the initial ray or initial side. And then the other is considered, wherever it resides, it's considered to have swept through an angle from the initial side to the terminal side. So the measure of the angle is really the same as with a geometric angle, but the direction matters. And most significantly, we show that by evaluating it. Suppose this is a 40-degree angle. Since I'm locked onto the Cartesian plane with my initial side, that means that the terminal side is free to go in either direction. So the same thing, I could have swept 40 degrees in the opposite direction, and had I done that, I would be looking at a different angle, even though the measure is the same. So in geometry, it's all about what's the same between two angles that may be oriented differently in space. But in trigonometry, they are different, and we are going to evaluate them as different. We're going to look at how they're the same, but we're also going to make a lot of use of how they're different. So notice that since I've gone in two different directions, I need a way to denote that. Turns out we're going to use the phrase, or we're going to use, well, this would be a counterclockwise, right? The orange angle goes counterclockwise from the initial side. So the counterclockwise angle we call positive. So it's a positive 40 degrees. The angle that went the same distance in a clockwise position or clockwise direction is considered a negative angle. So this would be a negative 40 degree, and the orange one would be a positive 40 degree angle. So they're different even though their measure is the same. Another way that trig angles differ from geometry angles is the units in which they're measured. So in geometry, you got really comfortable working with degree measure. In trigonometry and calculus, you'll evaluate angles in degrees, but also in radians. So let's look at degrees first, have a chat about that. You know that all the way around a circle is 360 degrees. And if you imagine a initial side locked on the x-axis with a vertex at the origin, then the terminal side of an angle, say here, well, I don't like that, say here at 135 degrees. Okay, I still don't like that. There we go. So 135 degrees, what that means is a complete circle is divided into 360 tiny little slivers of pie pieces, all equally sized all the way around. And for an angle on the unit circle, or excuse me, on the Cartesian plane, to have a measure of 135 degrees, it means that the angle, the terminal side of the angle, swept through 135 of the 360 degrees. This is useful to know because it gives us an idea of what percentage of the circle the angle has already used up. So if I took 135 degrees, divided it by 360, I could say that 3/8 of the circle is used in making this degree, or excuse me, this angle. The remaining 5/8 would be on the other side of the terminal ray, or terminal side. Okay, so that's useful enough. Let's compare this to radians. You already know how many radians to go all the way around a circle. You may not know that you know it, so let me show you that you know it. Imagine that you, excuse me, drew a circle with a radius of 1. The circumference is 2 pi r, but if the radius is 1, then the circumference is 2 pi. And so all the way around a circle in radian measure is 2 pi units, 2 pi radians. That means we could describe halfway around as pi radians. Or we could describe the angle 135 degrees, which is 3/8 of the way around. We could describe that angle in radians as 3/8 of 2 pi. 2's cancel, so that would be 3 pi over 4. So the angle that we call 135 in degrees, we're going to call 3 pi over 4 radians. What does that mean? That means that if I take 2 pi, if I take all the way around the circle and divide it into 4 equal pieces, I'm sorry, let me back up. If I take halfway around, pi, halfway around, and break it into 4 equal pieces, then I'm looking at 1, 2, 3, 4 equally sized pieces of pies in 180 degrees, or in 1 pi. And 3 of those, 1, 2, 3 of those, takes me to exactly 135 degrees. So this angle is at 3 pi over 4. Divide pi into 4 equal pieces, take 3 of them, and I end up there. And this may seem way complicated and like, why would you ever switch from degrees? It's only because we're so used to working in degrees. But as you get better at radians, you'll see and learn to like them a lot more because they're easier to work with. It's easier to figure out 3 pi, divide pi into 4 and take 3 of them, trust me, than it is to work with 135 degrees as we move farther and farther in math. All right, sales pitch is over. Let's look at one more way that the comparison between degrees and radians is really helpful. We know that 360 degrees is all the way around the circle. That's all 360 of the tiny little pieces of pie around the circle. And I don't mean pie like this, I mean pie like you cut a pizza. Let's say pizza. All 360 of the tiny little slices of pizza around the pizza. But to go all the way around the pizza in radians, it's 2 pi units. So I can say that 360 is equal to 2 pi radians. That's pretty convenient because when you have two different measures, two different units that are equal to each other, you have a conversion factor. And we'll make use of that conversion factor a lot. In fact, there's an easier way to work with the conversion, or an easier factor to work with, and that's taking advantage of the fact that only halfway around is pi radians, but only halfway around in degrees is 180 degrees. So let's see if that's true. Let's see if 135 degrees is indeed equal to 3 pi over 4 radians. Well, if I start with 135 degrees, and I multiply, just like you do in chemistry with a conversion factor, if I multiply by 360 over 180, 180 over pi, right? So 180 degrees divided by pi radians equals 1 because they're the same thing. They're both the same unit, the same distance, even though they're in different units. So it's a conversion factor, but it's also equal to pi radians over 180 degrees. They're both equal, so they're equal, and they're worth 1. So if I start with 135 degrees here and want to know how many, or want to convert to radians, all I have to do is use one of these factors that lets me cancel the units of degrees. That's going to be this one because it puts pi radians in the numerator, and it puts 180 degrees in the denominator. So now I can cancel the unit of degrees, and when I finish up my math, I'm left with 135 over 180 times pi radians. But 135 divided by 180, well, if 135 divided by 360 is 3/8, then 135 divided by 180 is 3/4 pi radians. And you can see that 3/4 pi is the same thing as 135 degrees. So let's do a few more conversions. Let's look at negative 30 degrees, and we want to convert this to radians. Well, first let's figure out where we are. So negative 30 degrees, I could give the answer in negative radians. That works. Or I could give the answer in positive radians. So if negative 30 goes here, then the other angle that leads to negative 30 in the positive direction would be 330 degrees. So let's do both of them. Let's start with negative 30 degrees, and we want to convert that. So I'm going to use the conversion factor that puts 180 degrees in the denominator. So I can cancel my degree units, and that gives me pi radians in the numerator. So 30 divided by 180, or negative 30 divided by 180, is negative 1 over 60. Sorry, negative 1 over 6. And then I have pi radians. So negative pi over 6. And we don't tend to write radians over and over and over. Negative pi over 6. All right, let's do it with 330. 330 degrees. This time it's positive because I went in the positive direction. Times pi radians over 180 degrees equals 11 pi over 6. I did it again. Third time's a charm. 11 pi over 6. Okay, now I bet you're thinking, how did she do that arithmetic in her head so fast? I got news for you. I didn't. Because I used the fact that radians are so much easier to figure out when you're working with a circle like this on the Cartesian plane. If I'm talking about pi over 6, I'm dividing pi into 6 equal pieces. That means this one has to be divided into 3, 1, 2, 3. This one has to be divided into 3, and so I have 1, 2, 3, 4, 5, 6 equal pieces of pi. On the other side, I would do the same thing. So if I have 6 on top and 6 on the bottom, that means one time around in pi, or with 6 in the denominator, means I have 12 pieces around the circle. If one of them got used up, making negative 30 degrees, then how many are left? 11 of the 12 pi's, 11 pi over 6. Much easier to work with when you do the kind of work that we're going to be doing. All right, one more example converting in the other direction. We want to convert 2 pi over 3 to degrees. So I'm going to start with 2 pi over 3, and then I want to multiply by something that lets me cancel my pi units. So that's going to be pi radians over 180 degrees. And so now my pi's cancel. This would have been pi radians. My radians cancel. And I have 2 divided by 3 times 180. Well, 180 divided by 3 is 60 degrees. So I'm looking at 120 degrees. Easy enough to do. And one last little thing having to do with this example. If going backward 30 degrees takes me to here, see if I can draw that better, takes me to right there, the terminal side of my angle. If going backward 30 degrees and forward 330, if I end up in exactly the same place for both angles, we call those coterminal. Coterminal angles. So if I go forward pi over 4, so that took me to here for pi over 4, that's divide pi into 4 equal pieces and use one of them. Then if I go backward, well, if there are 4 divisions on top and 4 on the bottom, that would be 8 of them. So I'm going to travel through negative 7 pi over 4 measures. So 7 pi over 4. So negative 7 pi over 4 and pi over 4 are coterminal angles because they end up in the same place regardless of how I got there.